Okay, so this is going to be the last chapter or the last video in this differentiation chapter, and we're going to be looking at modeling. So we've looked at stationary points and we allowed us to find like the maximum and minimum points, and that not only works for functions or graphs, it actually works for different models where the model is increasing or decreasing. So let's take a look at this one here. So we have a closed cylinder which has a total surface area of 600 pi. Show that the volume of the cylinder can be given by this formula. So first things first, with this type of question, we always want to sketch it out if there's no sketch given. So a cylinder like this, okay, and so let's label some of the stuff. Let's say this is the height, so let's call this h, and let's call this one the radius. So the total surface area is 600 pi, right? So 600 pi is equal to, and we need to find it in terms of r and h. So we have the top part is pi r squared, and this top and bottom, so 2 pi r squared, plus the cylinder itself, so it'll be 2r pi h, like this. So this is the surface area equation. Now the volume equation, V is pi r squared h, that's the volume of a cylinder. As you can see, you notice here there's no h term, right? So that means that they substituted this h term, gotten rid of it. So from this initial one, let's rearrange for h. So 600 pi minus 2 pi r squared is 2 pi r h. We can cancel some terms, so we can say that cancel, 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 and then we can divide by 2r, so h is going to give us 300 over r minus r, just r, like this. Okay, so that's what our h is going to be, which I'm now going to substitute into this position to get v. So v is equal to pi r squared, 300 over r minus r, which I can expand the bracket, so you can get 300 pi r minus pi r cubed. So that's what they wanted in part A. Right, in B, they're asking us to find the maximum volume of this cylinder. So whenever you'll see the word maximum or minimum, it means it says the first derivative is equal to 0, it's a stationary point, and then you can look at the second derivative. So that means we have to find the first derivative first, so we will differentiate this volume with respect to r. Okay, that's the only variable in this equation. So that's going to give us 300 pi minus 3 pi r squared. Remembering pi is just a number, right? So just treat it like a number. And we are equating this to 0 because we're trying to find the maximum, which is a stationary point. So that will give us 300 pi is equal to 3 pi r squared. Cancel, cancel. R squared is 100, and r is going to be plus or minus 10, but it can only be 10, right? Because r is a radius, it can't be a negative number. So we found, they're asking us for the maximum volume. What we found is the radius at the maximum volume. So to find the maximum volume, again, we just have to plug it back into this initial equation. So V is going to be equal to 300 pi times 10 minus pi times 10 cubed. We're going to get 3000 pi minus 1000 pi, which is 2000 pi, like this. That's the maximum volume this cylinder can be. They haven't asked us to show that it's a maximum, they just said find it. So if they asked to show it, that would mean we would have to differentiate this term again one more time, and then plug in r as 10, and it will hopefully be less than it'll be a negative number that shows that it's a maximum value. Let's try this one here. So we have a sector of a circle which has an area of 100 centimeters squared. Show that the perimeter is given by this formula. So it's a sector, so let's think of the equations for a sector. So area is half r squared theta, right? Where theta is this flat angle here. And so what we can say is this is equal to 100. Right, we're trying to find the perimeter. So the perimeter of this sector is going to be r plus this length here. And this length is going to be r theta. So this is going to be, P is going to be 2r plus r theta. Now you look at what they want you to make, and you can see there's no theta value here, right? So we're going to have to substitute the theta value. So from here, rearranging for theta, so half r squared theta is 100. So theta is going to be 200 over r squared, which I'm going to substitute into here. So P will be 2r plus r times 200 over r squared. Cancel, cancel, and you're left with P is 2r plus 200 over r. Okay, so just think about what variable they do not have in that equation. B is asking us to find the minimum value of the perimeter. So once again, if it's minimum, we have to differentiate this. So dp by dr in this case, that's the only variable. So this is going to be equal to 2r plus 200 times r to the minus 1. So differentiating that, we'll get 2 minus 200 r to the minus 2. And you equate that equal to 0 because its minimum is also a stationary point. So 2 is equal to 200 over r squared. R squared is equal to 100. Therefore, r is also 10 again. And to find the minimum perimeter, once again, we just plug this 10 into this initial perimeter equation instead of r, and you'll be left with the perimeter value, or the minimum perimeter value. Let's just try one final one. So this is a bit more difficult. So we have a cylindrical biscuit tin, and there's a closed fitting lid which overlaps the tin. So this lid will overlap it, and the tin's height is 1 centimeter. The radii of the tin and the lid are both x centimeters, and the tin and the lid are made from a thin sheet of metal with surface area 80 pi. So the total surface area is 80 pi, and there's no wastage. And they're asking us to find or show the volume equation. So first things first, let's create the volume equation. Volume is pi, instead of r is x squared times the height. Let's call this tin height h, pi x squared h. And we can create the area equation. So 80 pi is equal to the total surface area, okay? So let's look at the tin first. So the surface area of the tin would be 2 pi x h plus, there's a bottom of the tin, right? So that's going to be pi r squared, so pi x squared. That's the surface area of the tin. Now the lid, so there's a top as well, that's 2 pi x squared, another one. There's also the overhanging part, right? So that's going to be pi, 2 pi x times the height, which is just 1. That's the height of the overlapping part. So let's cancel. Let's do a bit of cancelling. So cancel, 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 cancel. So we'll get that 80 is equal to 2xh plus 2x squared plus 2x, like this. As you can see, we have to rearrange. There's no h term here, right? So we're going to have to substitute for h. So 80 minus 2x squared minus 2x over 2x is equal to h, which I'm going to substitute into this h position here. So v will get pi x squared multiplied by 80 minus 2x squared minus 2x all over 2x. As you can see, you can start cancelling out some terms. So x, well, let's just leave it like that. So let's multiply by x squared and divide by 2. So we get 40 pi x minus pi x squared minus x cubed, like this. Okay, so we get the volume that they want us to show. B, given that x can vary, use differentiation to find the positive value of x for which v is stationary. So they told us that v is stationary, which means that we should differentiate it with respect to x, dv by dx, meaning we get, so this is pi as well here, meaning we get 40 pi minus 2 pi x minus 3 pi x squared. And that is equal to 0 because it's a stationary point. Now we just have to find the x when it's equal to 0. So we'll have 3x squared plus 2x minus 40 is 0, cancelling out the pi's. And as you can see, it's a quadratic formula. So I can factorize it. 3x, x like this. This will be minus 10. This will be plus 4. So x is going to be either 10 over 3 or x is going to be negative 4. But remember, x is a distance, right? And it can't be a negative distance, so it can't be this negative 4. It's going to be 10 over 3. So that's the positive value of x for which v is stationary. C, prove that this value of x gives a maximum value of v, which means that I need to differentiate it one more time. So d2v by dx squared. So differentiating this term here, which is the first derivative, we get minus 2 pi minus 6 pi x. And I'm now going to plug in 10 over 3 into here. So minus 2 pi minus 6 pi times 10 over 3. What do we have there? This is minus 2 pi minus 20 pi, which is minus 22 pi, which is smaller than 0, so therefore we know it's a maximum value, like this. And finally, it says find this maximum value of v. Well, we got that the maximum occurs when x is 10 over 3, right? So therefore, I can plug it into my v equation, which I found earlier, or which I gave you earlier, this one here, and that will give you the maximum value of v. So you guys can do this later on, it's just literally plugging it in. As you can see, I'm using the fact that the first derivative is equal to 0 will give us a stationary point. If they ask me to prove that's a maximum minimum point, I use the second derivative to show that it's a maximum minimum point. So this is the end of the differentiation chapter. It's just the basic rules, but it's looking at pure 1 differentiation. In pure 2, the differentiation techniques get a bit more difficult, so maybe take a look at those videos just for some more advanced differentiation methods.